There is a stone on the floor of my old laboratory in Paris, gray, unremarkable. I used to step over it every morning on my way to the bench. I never once thought about what was happening inside it. Every mineral contains trace amounts of uranium. Every stone floor, every granite countertop, every stretch of bedrock beneath every city you've ever walked through. And inside each of those atoms, right now, something is happening that has never stopped, not for a single second in 4.5 billion years. I want to be precise about that, not dramatic, precise. The uranium in the ground beneath you is not sleeping. It is not inert. It is mid-process. It is breaking apart this second, releasing energy, becoming something else, and in doing so, it is warming the planet from the inside, and has been since before the first living cell divided in the first shallow ocean. That is not a metaphor. That is geophysics. Most people, when they hear uranium, think of something human. Bombs, reactors, Chernobyl, yellow warning signs. They think it's a thing we discovered and then contained. But uranium was never waiting for us to find it. It has been doing exactly what it does right now for longer than Earth has had continents. We arrived late. We gave it a name. We did not change what it was. Let me tell you what it actually is. A uranium nucleus is large, too large to stay stable. It has 92 protons crammed into a space smaller than you can meaningfully visualize, and the forces holding them together are in permanent tension with the forces trying to push them apart. The nucleus isn't broken, but it isn't at peace either. It sheds, periodically, without any external trigger, without any change in temperature, or pressure, or chemical environment. It ejects a piece of itself. That piece is called an alpha particle. 2 protons, 2 neutrons. The nucleus of a helium atom, launched outward at roughly 5% the speed of light. Not a wave, not radiation in the invisible, ghostly sense people imagine. A physical object, moving fast, carrying kinetic energy. And here is the part that matters. The atom that lost it is no longer uranium. Lose 2 protons, and you've changed the element. That's what an element is, defined entirely by its proton count. Uranium-238 ejects an alpha particle and becomes thorium-234, a different element, different chemistry, different behavior, and thorium-234 is also unstable, so it decays too into protactinium-234, which decays into uranium-234, a lighter isotope of uranium, still unstable, which decays into thorium-230, then radium-226, then radon-222, then polonium-218, then through several more steps until you reach lead-206. Lead, stable. The process stops there. I want you to sit with that chain for a moment. Uranium doesn't decay once and stop. It decays 14 times. It produces 14 different elements before it reaches stability, each one radioactive, each one contributing its own emissions, its own energy, its own behavior. It's not a single event, it's a dynasty, each generation unstable, each one transforming into the next, over billions of years. Radium is in that chain. My radium, the element I spent years extracting from pitchblende, processing ton after ton of ore in a leaking shed in winter, because we couldn't afford a proper building. My radium is uranium's great-great-granddaughter. When I isolated it, I wasn't discovering something alien to uranium. I was pulling one thread out of a lineage that had been running since the solar system formed. I didn't know that then. I learned it gradually, and when I understood it fully, I had to sit with the feeling that I had been holding something ancient without knowing the scale of what I was holding. The half-life of uranium-238 is 4.47 billion years. Earth is 4.5 billion years old. That is not a coincidence to be impressed by. It's a physical consequence. Radioactive isotopes with short half-lives decay quickly and disappear. Anything that was here 4.5 billion years ago with a half-life of, say, 10 million years is simply gone now, completely decayed to stability, leaving no trace in the geological record except its daughter products. Uranium is still here because its half-life is long enough that only half of the original supply has decayed. The other half is still going. Right now, in the ground. This is what I mean when I say uranium is alive inside the Earth. I don't mean it biologically. I mean it is mid-process. It is not finished. The transformation that started when this planet formed from a collapsing cloud of stellar debris has not completed. We are living on the surface of an ongoing reaction, and the Earth is using that reaction. When I first understood the scale of heat released by radioactive decay, not just in my laboratory samples, but across the entire volume of the Earth's crust and mantle, I remember doing the calculation twice because I didn't trust the first result. The numbers are staggering. Uranium, thorium, and potassium-40, decaying continuously through the entire interior of the planet, produce roughly 20 terawatts of heat. Continuously, right now, every second. That accounts for approximately half of Earth's total internal heat. The other half is primordial, heat that has been bleeding outward since the planet formed and was molten, and has not yet fully escaped. But half of what keeps this planet's interior hot is being generated fresh, constantly, by radioactive decay. What does that heat do? It keeps the mantle from solidifying. A solid mantle doesn't convect. A mantle that doesn't convect doesn't drive plate tectonics. Without plate tectonics, you don't get the movement of crustal plates, no mountain ranges being pushed up, no ocean floors being pulled apart, no subduction zones recycling crust back into the mantle, no volcanic activity releasing gases that shaped the early atmosphere. The geography of this planet, every coastline, every mountain range, every ocean basin, is partly the result of heat generated by uranium decay underground. I want to be careful here because geophysicists still debate the exact proportions. The 50-50th split between radiogenic and primordial heat is the current working estimate. It is not settled. Some models suggest radiogenic heat contributes more, some suggest less. The measurements are genuinely difficult, but the direction of the conclusion is solid. A meaningful fraction of Earth's internal energy comes from atoms breaking apart in the mantle and crust, and it always has. The shape of the continents is partly a nuclear phenomenon. That sentence is accurate. It's just not how geology is usually taught. Now, how do we know any of this? We can't drill to the mantle. The deepest borehole ever made, the Kola super deep borehole in Russia, reached about 12 kilometers before heat and pressure made it impossible to continue. The mantle starts at roughly 30 kilometers. We have never directly sampled it, so how do we measure uranium decay happening inside the Earth? In 2005, a detector called KamLAND, located in a mine in Japan, buried under a mountain to shield it from cosmic ray interference, detected something called geoneutrinos, specifically electron antineutrinos produced by beta decay in uranium and thorium chains deep inside the Earth. A neutrino passes through matter almost without interacting, through the entire Earth, through 6,000 kilometers of rock, iron, mantle, crust, as if it isn't there. Occasionally, rarely, but measurably, one will interact with something in the detector. KamLAND caught enough of these interactions to confirm, directly, that radioactive decay is happening inside the Earth right now. Not inferred from surface heat flow measurements. Measured. A particle produced in the mantle, which traveled through the entire planet, was detected. I find this genuinely strange, and I say that as someone who spent her career studying radioactive emissions. We can detect a particle that has passed through the entire interior of a planet, and we cannot yet make a precise map of where in that interior the decaying is concentrated. The spatial resolution of geoneutrino data is still low. We know the signal, we can estimate the total. We cannot yet say exactly whether a given portion of the signal comes from the lower mantle or the deep crust. The physics of detection doesn't yet give us that precision. That irritates me in the productive sense. It means the experiment has been done and the next experiment hasn't been built yet. There is one more thing I want to tell you about, and it unsettled me when I first encountered it. Uranium doesn't just sit evenly distributed through the Earth's interior. It moves. Groundwater dissolves uranium compounds in certain oxidation states and carries them through rock. Over geological time, uranium migrates and concentrates. It accumulates preferentially in continental granite. It's not uniformly distributed, it's patchy, localized. In some places it's remarkably dense. 1.7 billion years ago, in what is now Oklo, Gabon, in West Africa, a uranium ore deposit became concentrated enough and wet enough. Groundwater served as a moderator, slowing neutrons, that it reached a critical configuration. It sustained a nuclear fission chain reaction on its own for hundreds of thousands of years, a natural nuclear reactor, no engineers, no control rods, no containment building, just uranium, water, and geometry. We discovered this in 1972, when a French physicist, analyzing uranium ore from Oklo, noticed that the uranium-235 fraction was slightly depleted, not by natural decay, but by fission. The isotope had been consumed. When they traced it back, they found the reactor zones, 16 of them, and were able to reconstruct what had happened. The reactor would run, heat the water would boil away, the reaction would slow, the water would return as the rock cooled, and the reaction would start again. It pulsed, roughly a 30-minute cycle, for hundreds of thousands of years. Why can't this happen today? Because uranium-235, the fissile isotope, the one that sustains a chain reaction, has a half-life of only 700 million years. 1.7 billion years ago, it made up about 3% of natural uranium. That's enough to go critical under the right conditions. Today it's 0.72%. Not enough. The window has closed. The Earth ran that experiment, and the fuel ran out. I want to say something plainly about Oklo. It is not just a curiosity. It is evidence that nuclear fission is not a human invention. It is a natural process that the Earth discovered first, ran for hundreds of thousands of years, and then stopped when the conditions changed. We didn't invent nuclear reactors. We rediscovered a process the planet had already completed. That reframing matters to me. I spent my career in a field that was often described as humanity reaching into the unknown. Oklo suggests we were reaching into something the Earth had already done. The unknown was, in some cases, simply history we hadn't read yet. Now I want to say clearly what we don't know, not as a disclaimer, as the actual current state of the science. We don't know the precise uranium abundance in Earth's lower mantle. Different geochemical models give significantly different estimates, and the geoneutrino data isn't yet precise enough to adjudicate between them. We don't fully understand the mechanism by which uranium concentrates in continental crust, rather than staying distributed through the mantle. The general process, uranium being more soluble in silicate melts that form crust, is understood, but the detailed geochemical pathway is still being worked out. There's something called the missing heat problem. Some geophysical models, based on what we know about the abundances of radioactive elements and their decay rates, predict more heat coming from Earth's interior than we can account for with current measurements. Either the models are wrong about abundances, or the heat flow measurements at the surface are incomplete, or there's a source of heat we haven't identified. Nobody is comfortable claiming the third option without more evidence, but it hasn't been ruled out, and on a longer time scale, as uranium continues to decay over the next several billion years, the radiogenic heat contribution will decrease. Earth's mantle will cool. Plate tectonics may slow, eventually may stop. The magnetic field, which depends on convection in the liquid iron outer core, which itself depends partly on the thermal gradient maintained by radiogenic heating. The magnetic field will weaken. The time scale for this is hundreds of millions to billions of years. It is projected, not observed. But the physics points in one direction. I want to be honest that I find this sequence of consequences striking, not because it's alarming on human time scales. It's irrelevant. But because it reveals something about what we're standing on. The stability of this planet's surface. The relative calm of the geological moment we happen to occupy. It is a temporary condition maintained by a process that has a finite supply of fuel. Every element heavier than iron in the universe was produced inside a star that later exploded. Uranium didn't form here. It formed in the violent collapse of a stellar core, a supernova, somewhere in the galaxy before our solar system existed. When that star exploded, it scattered its contents into space. That debris became the molecular cloud that eventually collapsed into our solar system. Earth formed from it, and the uranium that arrived in that cloud has been decaying ever since, continuously, without interruption, through the formation of the planet, through the origin of life, through every extinction, through the entire span of human existence, through this moment, as you watch this, it will still be decaying when there are no humans left to think about it. That is not a grim thought, it's a scale thought. We spend a great deal of time treating the ground as though it was simply there, fixed, background, beneath notice. But it is a surface, resting on a planet in slow transformation, driven partly by the same nuclear process. I first measured with instruments I built myself from salvaged materials in a laboratory that was essentially a converted shed. The stone on the floor of that laboratory was not just a stone. Every mineral grain in it contained nuclei in mid-decay, producing particles that passed through my shoes, through my feet, through the floor, through the ground below, emerging the other side of the planet, having interacted with nothing. I stepped over it every morning. I didn't know what I was stepping over, neither did anyone else. That's what made it worth understanding.